Okay, class, welcome back. Hopefully you guys you're happy about your exams, and we can move on forward to chapter 7 entitled Chemical Reactions. All right, so this is lecture 1. So in this chapter, we're going to learn about all sorts of different kinds of chemical reactions, but I wanted to start off with not the most basic one, but one that we're really familiar with, and that is combustion. In general, a combustion reaction is any type of hydrocarbon and oxygen. Those are the reactants, and they react together. They react together to form carbon dioxide and water. So this example that I have right here is the combustion reaction that takes place in the engine of your car, and you have octane, all right, which is it's C8H18. That's your hydrocarbon, and hydrocarbons are what they sound like. They're a molecule that's just made up of carbon and hydrogen. Okay, fossil fuels, those are all hydrocarbons. And then we have oxygen right here. Now you'll see that each ball represents an oxygen atom, and since when we talk about oxygen in nature, it's always going to be O2, all right? Right, because oxygen is a diatomic. Now these two guys are going to combine. They're going to react with a little bit of heat, all right, and they're going to form carbon dioxide and water, H2O. Okay, so this is carbon dioxide, one carbon, 2 oxygens, and then water, 2 hydrogens, and 1 oxygen. Okay, so a combustion reaction is anything that you see in this chapter or in the world where you have a hydrocarbon, you have oxygen, plus a little bit of a heat source that yields CO2 and water. Okay, the burning of a candle is also a combustion reaction. So there are several indicators of chemical reactions. So you're going to need to know those before we can even talk about different types of chemical reactions. The first is a color change. All right, so if you see any type of color change, that's going to be an indicator of a chemical reaction. Remember, chemical reactions, those are not phase changes. All right, the before and after for chemical reactions are completely different. Phase changes before and after, essentially, the molecule is the same. It's just that the phase that the molecule in is different. All right. Formation of a solid is indicator of a chemical reaction, and I have here is a picture of it right here. So a lot of times, and in lab you would normally do this, but since you don't have lab, you're not going to see it. But whenever you mix two things that are in solution, and then you end up having solid, we call it crashing out. All right. So that's a precipitate. That's what that solid is called, a precipitate. It forms, okay, that is a precipitation reaction. It's a specific kind of reaction, but nevertheless, it's still a chemical reaction, so that is also an indicator of a chemical reaction. The formation of a gas is also an indicator. The emission of light, all right, and then also the emission or absorption of heat. And if you were in lab, you would get to see this with your own eyes and get to feel it with your hands, but it's kind of cool when you mix two things together and then all of a sudden the reaction gets really cold. And that's because it's an endothermic reaction, and that reaction is absorbing heat from its surroundings. So these are the 5 main indicators of a chemical reaction. Just to be clear, I don't want anybody to be confused about, let's say, water boiling, right? Because even though water boils and it forms bubbles, gas is evolving, but this is not a chemical reaction. It's just a phase change from water in its liquid phase to water in its gaseous phase, okay? It's still water before and after. So just a little caveat there. So it's important for you guys to understand chemical reactions really fast and how we write them and represent them. On the left-hand side, we have the reactants. And then also after every single reactant, a lot of times you'll end up seeing a subscript, like something in parentheses in a subscript, and that is the state of the reactant, and we'll talk about that in a second. But then we have this arrow right here, which indicates that the reactants react to form the products, which are always on the right side of the equation. And again, with the products, oftentimes we have the state indicated as well. And we often specify the state of each reactant or product in parentheses next to the formula. So what are the states that you need to be familiar with? Well, it's all the states that we've talked about, solid, liquid, gas, with one more, all right? G is gas, L is liquid, S is solid, and AQ, that's something that we haven't seen before, but that means aqueous, all right? So if you see AQ after something, that means that whatever that reactant or product is, it's soluble in water. An example of this would be sodium chloride, right? AQ, right? We all know that salt is soluble in water. Okay, so, and we'll talk about what happens when, we'll talk about what happens when we actually dissolve salt in water. But if you see something like sodium chloride and then a subscript AQ next to it, that means that that salt is in solution. It's in a water solution, aqueous solution. Okay, so it's also important for you to understand how to write chemical reactions from reading them in a paragraph. So for example, the reaction occurring in a natural gas flame is reacting with oxygen to form CO2 and water. So we can write this reaction in the following equation. So we'll just go ahead and change that. So we have the reaction occurring in a natural gas flame is methane, so we're going to write CH4 that reacts with oxygen to form. So whenever we see to form, that means whenever we see to form, that's arrow. Okay? To form CO2 plus H2O. Okay? So that's how we would write that out. So here you go. So we have the reactants right here, methane and oxygen, and the products CO2 and H2O. Oops. Sorry. I'm just going to keep going with this. Okay. With the states included. Now, the states weren't ever indicated up here. Okay, but, well, it kind of was with the natural gas flame. So you can sit back and say that we know that if it's natural gas, we're going to have CH4 and then subscript gas. All right. So instead of gas, so we'll just do subscript G plus O2. Oxygen gas, again, is a diatomic, so G as well. All right. Again, arrow again. And then carbon dioxide, we know, is a gas. And then H2O, and turns out, sorry, I'm running out of room. I'm going to write G here as well, because H2O it's going to be water vapor. So here it is right here, so you can see everything that I just wrote. All right, but we know what the subscript G means. So you'll notice from this equation we have, again, we have methane. And I'll write this in red. So we have CH4, here, I'll write up here. We have CH4, right, plus O2 goes to CO2 plus H2O. Now, it's important for you guys to understand that we actually have to balance this chemical reaction, because what turns out, as we know from the law of conservation of mass, is that we cannot lose atoms or mass in a chemical reaction. Things can't just disappear. So if we have a certain amount of carbon atoms, let's say, on the reactant side, we're going to need to have that many amount of carbon atoms on the product side as well. Same thing goes with hydrogen and oxygen for this particular reaction, right? Because those are the only elements that are in this. So it's important for you guys to understand how to count and how to balance. So first you're going to ask yourselves how many oxygen atoms are on each side of the equation. Well, as you can see here, I wrote it up here, O2. Here are the 2 oxygen atoms right here. So there are 2 on the reactant side. But then if we go over to the product side, again I wrote up here, here, and it's also here, you have CO2 and you have H2O. All right. CO2, that's the 2 oxygen atoms right here. And then H2O, that's 1 oxygen atom. So we have 3 oxygen atoms on the product side. So the way that this chemical reaction is written here and represented here and written down here with the phases, we somehow magically gained an oxygen atom on the product side. And that cannot happen, right? That's not how things work. So you're going to have to balance the equation in order to make sure that the oxygen atoms on the right equal the oxygen atoms on the left. Okay, so same thing with the hydrogen atoms. You'll notice on the left side, the reactant side, within methane, okay, we have 4 hydrogen atoms. And then on the product side, the only place that we have hydrogen atoms is in water, and then we have this represented just by 2 hydrogen atoms. So we can't lose 2 hydrogen atoms from the reactants to the products. So in order to correct, and you'll notice too that just to make sure that we have 1 carbon atom here on the product or reactant side and 1 carbon atom on the product side. So even though carbon is balanced, hydrogen and oxygen is not. So in order to correct these problems, you have to create a balanced chemical reaction to appropriately represent what's actually going on right here. So in order to balance this chemical equation, you have to insert coefficients, okay? You can't change the subscripts, right? That's a big no-no. But the only thing that you can do is change coefficients in front of the chemical formulas as needed to make the number of each type of atom in the reactants equal to the number of each type of products. The equation is now balanced, you'll notice, because the number, after putting a 2 here and a 2 here, because the numbers of each type of atom on both sides of the equation are now equal. All right, so if you'll take a look really fast, now we have 4 oxygen atoms, right, because there's essentially 2 O2 molecules, so that's 4 oxygen atoms here. And then you'll notice here by putting a 2 in front of H2O, right, we already have 2 oxygen atoms, right, here and here. And now we have 2 more from adding the coefficient of 2 right here in front of water, giving 2 water molecules. So collectively we have 4 oxygen atoms, so we're good there. And then if we want to take a look at, we'll say hydrogen, here we have 4 hydrogens. We didn't add anything to the front of methane, so we have 4. So I'll put 4H. All right, but since we added the 2 right here in front of water, now we have 2 water molecules, and each water molecule has 2 oxygens. So that's a total of 2 hydrogens. So that's a total of 4. So now we are completely balanced just by adding the coefficient of 2 in front of O2 and H2O. And this is just a breakdown of everything that I just said, so you can review that if you'd like. So again, balancing chemical equations all comes from the law of conservation of mass, saying that the total mass of products of the reaction is the same as the total mass of the reactants. But more specifically, it's that we can't lose or gain elements and atoms in a balanced chemical reaction. So in any chemical process, whatever atoms are present at the beginning of the reaction must be present at the end. Okay, so in order to write chemical equations, the reactants are always, again, on the left-hand side. and the products are always on the right-hand side. So here I have sodium, right? I don't have any phases here, but sodium reacts with chlorine to make sodium chloride. And you'll notice here that we have one sodium atom and one sodium atom. So technically, is it balanced, right? Sodium is balanced, so we're good here. But the problem is that we have two chlorines here on the reactant side and only one chlorine on the product side. So what are we going to have to do? We are going to have to put a 2 in front of NaCl to give us now 2 chlorine atoms. So now chlorine is good here and it's good here, but guess what? Sodium is now not, right? Because we have 2 sodium atoms right here. So what we're going to have to do is go back and then put a 2 here, and now sodium is also good. So collectively, sorry, I'm going to skip through that. Here it is. So this is your balanced chemical reaction, all right? And so that type of thought process is what you're going to need to have when we start going and balancing out more complicated chemical reactions. So here is, in a nutshell, how to write balanced chemical reactions, and then we're going to balance them. So what you're going to do is you're going to write a skeleton equation, okay? Skeleton equation by writing correct chemical formulas for each reactant and product. And you're going to have to review Chapter 5 for nomenclature rules, okay? So you're going to have to know what aluminum sulfate is so you can write out this appropriate chemical reaction. You are only allowed to add numbers in front of the formulas. You're only allowed to change the coefficients. You are not allowed to change the subscripts, all right? Changing subscripts is not allowed. In general, all right, most people will find they'll get their own method down, but in general, work from left to right, one atom at a time. And in long, complicated reactions, leave oxygen and hydrogen until last. And if polyatomic ions, okay, this is important, if polyatomic ions remain unchanged from the products to the reactants, you can balance that polyatomic as a group. And we'll go over an example in just a second. But you don't have to break up the polyatomic ion. You can balance it as a group, and that ends up being really, really beneficial. And then finally, you're going to use a common multiple approach when necessary, and we will talk about what that means in just a second. And then again, always go back and check your work and make sure that your final answer is correct. So, just to make sure you understand, you're going to balance the equation entirely by using the coefficients, all right? You're not allowed to change the subscripts, right? Because that changes the formula, and then that's not allowed. You are not allowed to change you're not allowed to change a correct chemical formula in order to make an element balance, so you can't change the subscripts. And you're also not allowed to add some real or imaginary chemical species to the right or the left side of the equation just to make everything balance out. You just can't add a water molecule, right? So you have to stay within the actual chemical reaction, and you can only change the coefficients. Again, I just want to make this point very clear. You're going to use your knowledge of the chemical nomenclature from Chapter 5 to write these skeleton equations, all right? And it's also really important for you to understand that the formulas of each compound must be correct in order for you to even go forward with balancing, okay? So if you get aluminum sulfate wrong, if you write for aluminum sulfate AlSO, we'll say AlSO, let's say if it's Al2SO4, right, that's not correct, right? That's wrong. So you need to make sure that you have this correct before you even get started. So here we go. We'll do a practice. For the reaction of solid aluminum with aqueous sulfuric acid, so that forms aqueous aluminum sulfate and hydrogen gas. So what are we going to do? So the first thing we're going to do is we're going to say solid aluminum, right? So for the solid aluminum, I'm going to write AL, subscript S plus, and then you'll see this is aqueous sulfuric acid. Now I gave you sulfuric acid, the chemical formula, because we didn't go over acids in the previous chapter because we had a time issue. So there it is right there, and I'm writing subscript aqueous, and then to form, so that's your arrow, and then aqueous aluminum sulfate. All right, so aqueous aluminum sulfate, so you have Al. Now, if you remember, aluminum is always a +3, and then sulfate, SO4, is always 2-. So we can't just combine those 1 to 1, right? We have to find a common multiple, which is 6, and then what you could also do is just, I'll just go ahead and say, so that means for every 2 aluminums, we're going to need 3 sulfate ions. So it's going to be Al2, SO4, subscript 3, okay? And that's going to be aqueous, so we're going to write subscript AQ, and then hydrogen gas, which is H2, because remember it's a diatomic, and then subscript G. So this right here is a skeleton equation, all right? It's a skeleton equation because it has all the correct compounds, but nothing's balanced, right? Because we have 2 aluminum, or we have 1 aluminum here, but 2 over here, right? So next thing we're going to do is we're going to have to balance it. So here it is right here. So I have it listed all right here so you can go through it, but the way that I like to do it is starting from the right to the left, okay? So what you can clearly see here is that aluminum, we have 1 aluminum on the reactant side, and we have 2 aluminums on the product side. So we're going to have to go over and write a 2 in front of aluminum, so that means aluminum is good, so do a little check mark above that. Then we're going to move over to the H2SO4. I'm going to wait to balance this hydrogen, and I'm going to look at SO4. All right, that's a sulfate anion. So what you're going to do is you're going to look back and you're going to ask yourself, does the sulfate anion, does the polyatomic anion stay intact on the product side? And the answer is yes, SO4, SO4. The only difference is that on the product side we have 3, and you can see we have 3 from the subscript right here. So that means we're going to need to have 3 in front of the H2SO4 to give us 3 sulfate anions. So I'm just going to go ahead and put a check here because we have 3 sulfate anions on the left and 3 sulfate anions on the right. Now finally we're going to hydrogen. Now hydrogen on the reactant side, we have a total of how many? We have 6 hydrogen, okay? On the product side, we only have 2. So we need to multiply it by something, right, to get to 6. So what is that number? It's going to be 3. So we're going to put a 3 right there. And now if we go back and look, everything, and I'll put a little check mark just to make sure, everything looks balanced. So I'm going to skip through these. This is something that you can look at on your own, but here is the entire balanced chemical equation. All right, and you'll notice I have 2, 3, and then 3. All right, and then this is also a slide just to show you that the products and reactants, the inventory of the atoms are correct, right? 2 aluminum on the product side, 2 aluminum on the reactant side. So you can go through that at your leisure if you'd like.